Is it starting yet? There you go. In this video, we are going to just do kind of like a general science introduction, and hopefully going to go through things pretty quickly because I want to go to lunch. All right, so in other classes, you've probably heard people refer to the scientific method as in this is the only way scientists do things. And that's not necessarily true that scientists always just kind of go through these things in a step-by-step manner. There are lots of scientific methods out there, and it's not, always necessarily as formalized as we lead you to believe. But it is a good way when you're starting out to kind of say, yep, these are the steps that we take for a scientific investigation. Because more or less, that's what we do. So we always start off with we have to have a question. We do some background research on the question to see like, hey, what do we already know? If you can look up the answer to your question on the internet and it's like, oh, okay, got the answer, and that answer seems like it's well supported, there's probably no reason to do an experiment. If you can't answer your question, but you kind of have a better idea, you make your hypothesis, then you test your hypothesis by doing an experiment, analyze your data, and then you report out and you make a conclusion, and then report to the world, hey, this is what I found out. I don't like this flowchart so much because in reality, science is more like this. Okay? You're constantly going around and around. There's no starting, there's no ending. Maybe sometimes you see somebody else's results and then you make findings based on that, or you make a new hypothesis based on their results, and that kind of gets you started. But it's a circular thing, and it's never done. Okay? I found this graphic on the internet, and I just figured when I was just trying to liven up my presentation with pictures, I thought it was interesting that it's all pretty much in order except for the last two. The researching your topic and the think of an idea obviously doesn't come before a conclusion. So if we put them in order, you should think of an idea first, then research your topic, then plan your experiment. And it doesn't have anything about a hypothesis in there. But that's okay. But yeah, those last two are out of order. Okay? Just making sure you understand the differences between some terms that get passed around. Okay? So we've already kind of talked about a hypothesis, which is your possible answer to a question. And it's like a one-time thing. Okay? You make your hypothesis each time for each experiment. A theory is like, I've made this hypothesis over and over, and I've looked at things several different ways, and oh my gosh, the apple always falls, and this is why I think why it happens this way every time. And I start gathering enough evidence together where I have a pretty good idea what's going on, and I have a new explanation for it. That's a theory. So scientific theory is not like when people say, oh, that's just a theory. A scientific theory is not just a theory. A scientific theory is based on hours and hours of different people working on testing hypotheses over and over again until these related hypotheses always get supported, and then finally we kind of pull them all together into one big theory, which explains things. A law doesn't explain anything. A law only describes what happens. Like, okay, things fall. That's a law. Okay? No, that's not the best statement of that law. Why they fall is the theory. Okay? So basically, a law just tells you what things do. It doesn't tell you why they do that, or it doesn't attempt to explain why. It just says this is what, how things are related. Oops. When we are looking at investigations, there are always three types of variables. There's the independent variable, which is what the experimenter changes on purpose, so they can see what it is, and we can think of the independent variable as being like the cause. There's the dependent variable that we think of as the effect. That's what happens because of what you already did. And then there are the control variables, or the constants, things you have to keep the same all the time. Okay? So those are the three types of variables, and we are going to be practicing in class how do you identify these different types of variables, because it's important that you're able to do that and that you understand it, because you can't understand scientific experiments if you're not able to figure out what's the independent variable, what's the dependent variable, what's the control variables. Okay? when we are writing a purpose for our experiment, a good purpose always says, how does the independent variable affect the dependent variable? How does the color of my clothing affect how hot I get? Okay, so that's, so the color of the clothing would be independent, the dependent would be how hot you get. A good hypothesis. So what makes something a good hypothesis? A good hypothesis is a statement. It's not a question. Okay? Saying what will happen to the ice cream as it gets hotter out is not a hypothesis. That's a question. A hypothesis is a statement that could possibly answer that question. A good hypothesis is clear. Everybody should know what you mean by it. It has to be testable. So it has to be something that you can then perform an experiment on. It has to mention the independent and dependent variables. So oftentimes it's written like below. If this happens, then this will happen. Not what if, but when, or you could say when independent, then dependent, if you don't like the if you think that sounds like a question. After you've made your good hypothesis, you have to perform a good experiment. A good experiment should be repeatable. It shouldn't work just because you did it and you knew what you were doing. It should work when anybody who knows what they're doing does it. Okay? And if it only works the way you want it to once, it's not a good experiment. A good experiment should be easy for anybody to follow, to be able to see what you did. So that, again, it goes back to repeatability. A good experiment has to be designed to test the hypothesis and nothing else. So you should only be testing the relationship between those two variables. You shouldn't be testing the relationship between a whole bunch of different things. A good experiment has control, which makes it a fair test, which means that when you see an effect, it's actually going to be caused by the independent variable and nothing else. So it couldn't be caused by other factors that you just didn't think of. When you go to write a good conclusion uses all of your available evidence. It uses only the available evidence. And the available evidence is what you came up with in your background information, and it's what you came up with when the data for your experiment. It only uses those things. A good conclusion is not based on your opinion. Okay, you don't get to say, well, even though the data shows this, I don't think that's true, and so my conclusion says otherwise. Okay, if you really feel it's not true, then you say, I think I need further study, and I'll just keep doing it until I try to prove it wrong, and maybe I never do. A good conclusion should be the answer to your purpose. Your purpose was a question. Your conclusion should answer that. Okay, and maybe the answer is, I still don't know, but it should address the purpose somehow. The last thing, because we're doing some measurements in class, I just wanted to spend some time addressing, the proper ways to measure something. And so when you go to make measurements, so let's say with a ruler, this is a millimeter ruler, which I need to make a little longer. Whoop. Come on. Don't you wish you could do that with a real ruler? We need to make sure we're using our tools properly. So with this ruler, the way we use it properly is we need to make sure 0 is on one end. Okay? When we make our measurements, we always measure to as much precision as we can. So when I look at this, okay, I can see that it's about 205. But that's not good enough. So I look really close and I see, well, it's not quite at 205. It's just past 204. And so when I write how far it is, I write 204. But it's not exactly 204 either. It's a little bit past. I can't see exactly where it is, and you're not all going to agree on where it is and where I say it is, but I'm going to say it's 204.3 because I think it looks like it's a little bit past 204. That's where I think it lies. Not everybody will agree on this last digit. This is called the uncertain digit. Everybody should agree that it's 204 something, but we're not going to agree what. That's the uncertain digit. We write it down. Everybody understands that when you make a measurement, that last digit's uncertain, and maybe it's really 204.2, and maybe it's really 204.4, okay, or 204.5, depending on what measurement. Your uncertainty might be bigger or smaller, but you always write down what that uncertain digit is. The last thing that we need to make sure we always write down when we're making a measurement is units. This is a millimeter ruler, so I'll write down millimeters, because 204.3 millimeters is a lot different than 204.3 kilometers, a lot different than 204.3 degrees Celsius. You always want to make sure you have those units written down, so there's no question about what you meant. Oh, gotta get rid of that ruler. When we are making measurements, we have to realize that sometimes there are going to be errors. Okay, we're trying to limit those errors as much as possible. We are trying to make measurements that are both precise and accurate. And so this picture kind of describes the difference between precision and accuracy. Being precise, like for example the ruler, has to do with using all the marks on the ruler and then estimating when it falls between the marks where it is. That helps you be precise, using like getting ever finer marks on that ruler. Talks about precision. Okay, if you're not precise, like on these bottom two, it just means that you're not reading things very carefully. Okay, if you're inaccurate, like these side ones are here, okay, the ones on the right hand side are inaccurate, it means that there's some sort of error that you're doing, like you're doing the error the same way all the time. This one, when you're not precise, okay, when you're not being precise like the bottom ones, it means that you have random errors. Sometimes you measure too big, sometimes you measure too small. Whatever's causing your errors, it's like a random thing and it's slightly different every time. When you're not accurate, it means that whatever you're doing wrong every time. Okay? If you're precise and not accurate, like in the same one. It's like you're measuring really closely, but you're measuring wrong every time. Okay? We want to try to make sure we're measuring correctly every time, and we're measuring as precisely as possible every time, like the top left one. Okay? So just to make sure you understand the differences between precision and accuracy. All right? That's all I have for you for today. Let's see, what do we get in? 12 minutes. All right? So hopefully this is helpful.